Hello dear students. In this video, we will be learning about bitwise operators in C. Bitwise operators, as the name suggests, bitwise, these operators perform on individual bits. They perform on individual bits of the numbers. So the operations are performed on the bits 0 and 1. Well, there are 6 bitwise operators in C language, and the bitwise operators as written here is the single ampersand symbol. Ampersand symbol stands for bitwise AND. This pipe symbol, vertical line, this pipe symbol stands for bitwise OR. Then we have this cap symbol, which stands for bitwise XOR. Then two greater than symbols written in quick succession stands for bitwise right shift. Two less than symbols stands for bitwise left shift, and this symbol tilde symbol stands for bitwise complement. To understand what is bitwise really, there is some prerequisite which I expect from GATE students. GATE students obviously know what is decimal equivalent and what is binary equivalent of number. For example, suppose I have int a equal to 10. Then what is binary equivalent of 10? It is obviously 1010. And if I have b equal to 12, what is the binary equivalent of 12? It is 1100. And I have one more variable c whose value is not yet defined. Now the expression that we have written is c should become equal to a and b. How do you read? The statement is c should become equal to a bitwise ANDed with b. A is bitwise ANDed with b. So actually a is 10, isn't it? And b is 12. But the operation will be done on the bits of a and b. So here I have shown the representation as a is 10 here. A is 10. So what is the binary equivalent of a? I have written it as 1010 as you see. Binary equivalent of a is 1010, that is 10. And b is 12. B is 12. So I have written binary equivalent of 12, which is 1100. We are now evaluating C is equal to A bitwise ANDed with B. So these two numbers, these two binary numbers are going to be bitwise ANDed. As you know, AND operator is exactly like logic gate and logic gate, which says that if both the bits, both the inputs are high, only then the result will be high. So if both corresponding bits are 1, then the output is 1, otherwise the output is 0. So if you bitwise AND these two bits, then 0 and 0 will be 0. Bitwise AND these two bits, then 1 and 0 will be 0 again. Bitwise AND these two bits, 0 and 1 will be 0 again. But 1 and 1 is going to be 1. So the result we have got is 1000, 1000. But that will not be the value of C. C will be, of course, C is 1000, but this is in binary form, isn't it? So what's the value of C really? C is 8, because 1000 in decimal is 8. Let's see one more example. Let's say that I have a code like this. Int a equal to 10, b equal to 12, a equal to 10, b equal to 12, and there is a variable c declared. The expression given is c is equal to a pipe b. This is a bitwise OR with b. A bitwise OR with b. So what is a? A is 10, but A is 10, but the binary equivalent of A is 1010. Further, B is 12, B is 12, but the binary equivalent of B is 1100. Now we are evaluating C is equal to A bitwise or B. A bitwise or B. So if you do 0 or 0 as 0 logic gates, as OR logic gate says, if at least one input is high, then the output is high. Otherwise, the output is 0. Now 0 or 0 is 0. 1 or 0 is 1. 0 or 1 is 1. And 1 or 1 is 1. Both inputs are high. So this is C. C is 1110. But this is in binary form. C in decimal form, as you all know, 1110 is 14. So C will be 14. Let's see one more example. Let's say we are working this time on XOR operator. So we have int A equal to 10, B equal to 12, C. And the expression we have given is C is equal to A cap B. This is A bitwise XOR with B. Now XOR gate, as the name suggests, XOR gate means that if both the inputs are different, then the output is high. So 1 XOR 0 is 1, 0 XOR 1 is 1. That means the two inputs are of different types. But 0 XOR 0 is 0, 1 XOR 1 is 0. If both inputs are same, then the output is 0. Let's see. We have A as 10. A is 10. So binary equivalent is 1010. Further, B is 12. So binary equivalent is 1100. And we are doing C is A XOR B. C is A XOR B. So let's see what will be XORing. 0 XOR 0. Both inputs are same. Then the output is 0. 1 XOR 0. Both the inputs are different. Output is 1. 0 XOR 1. 0 XOR 1. Both inputs are different. Output is 1. 1 XOR 1. Both inputs are same. Output is 0. So the value of C is 0110. But this is in binary form. C in decimal form, as you know, 110 is 6. Okay, let's see what is this right shift operator, or rather let's first see left shift operator. Let's see a simple code like this. We have A equal to, let's say we have A equal to 5 and we have B. Value of B is not given. Expression given is B equal to A left shift 1. A left shift 1. Now before I show you bitwise operation on this, because this is of course the operator we have written is bitwise left shift, but before I show the operation of that, let me tell you the meaning of this. The meaning of this is, in fact, B should become equal to A multiplied by 2 raised to 1. Whatever is given after left shift, this 1 was given, isn't it? So it is 2 raised to that number is multiplied with A. So this is A multiplied by 2 raised to 1. What if I would have given B equal to A left shift 2? Then B would have become equal to A multiplied by 2 raised to 2. So in general, if I write B is equal to A left shift I, where I is some number, then this means B will become equal to A multiplied by 2 raised to I, isn't it? Because anything left shifted with I means multiplying that number A with 2 raised to I. Let's see this in operation. What we have is A is 5. So what is binary equivalent of 5? Binary equivalent of 5 is 101. This is 5. But now we are evaluating B is equal to A left shift 1. What that means is bits of A, these 101 are bits of A, should be left shifted, should be left shifted, should be left shifted by one place, by one bit. So it means this one, the very first one will come one place to the left. This 0 will take over the place of this 1. The last one of our binary number will come at the place of 0. And there will be an additional 0 padded up on the extreme right, or rather LSB, least significant bit of the number. And this is the value of B. This is the value of B, 1010. But that means B in decimal form, 1010 is nothing but 10. B is 10. Come again. What was the expression? B should become equal to A left shift 1. What was the value of A? A was 5. But left shift by 1 means 5 is multiplied with 2 raised to 1. Tell me, isn't B equal to 5 multiplied by 2? That is 10. Hence proved that if A is left shifted by I, then A is multiplied by 2 raised to I. Let's see right shift operator. Suppose I have int A equal to, let's say, 10, and I have B. And I have given B should become equal to A right shift 1. Now, before I show you what is the operation, how this right shift operates, the meaning of this line actually means B will become equal to A divided by 2 raised to I. A divided by 2 raised to I. For instance, if I would have given B equal to A right shift 2 instead of 1, then it would mean B should become equal to A divided by 2 raised to 2. In general, if we write B is equal to A right shift I, where I is some number, then it means B will become equal to A divided by 2 raised to I. Remember this. Now let's see this in operation. A is 10, but the binary equivalent is 1010. And we are evaluating B equal to A right shift 1. A right shift 1. What that means is every bit of this number A will be right shifted by one place. Isn't it? Will be right shifted by one place. Now this 0 will be kicked off because there is no place after this. This was LSB, isn't it? So this 0 gets kicked off and gets lost. But this one will occupy, the second last bit will occupy the LSB. So 1 joins here, and every bit like this gets right shifted by 1. So we get 0 here, we get 1 here, and one additional 0 is padded. One additional 0 is padded in MSB, most significant bit. Hence, this is the value of B. B is 0101. See that B in decimal is 5, because 101 is nothing but 5. Have we proved enough? What we were trying to find out is B is equal to A right shift 1. And remember, A was 10. 10 when right shifted by 1 means B should become equal to 10 divided by 2 raised to 1. But 10 divided by 2 is 5. And that's exactly the value that we got. Now let's see the another operator called complement. Complement, as the name suggests, will work on bits of the number and make 0 as 1 and 1 as 0. Simple complement operator. For example, if I have int a equal to 10 and another variable b, and if I say b is equal to tilde a, this is complement of a. Now observe that tilde is an operator which is unary operator. It works only on one operand. It takes this value a, and every bit of a is complemented, and the resultant value is stored in the variable b. Now in this discussion, we will have to assume that the number a is stored as a 4-bit number. To make it easy, let's say our computer always stores any integer in 4 bits. Actually, it is very silly. 4 bits is very less width or very less space to store integer. But let's say that a is 10 and a is stored as a 4-bit number. You all know as gate students that we have the memory unit as byte, and every byte is 8 bits. So 4 bits is too less quantity I am taking. But let's imagine that a is represented as a 4-bit number 1010, which is binary equivalent of 10, and we are saying b should become equal to tilde a, that is complement of a. Now complement of a will be this 0 is complemented as 1, 1 is complemented as 0, 0 complemented as 1, 1 as 0. So this is the value of b, 0, 1, 0, 1. Hence b will be equal to 5. These are simple operators, bitwise operators, 6 operators. Now the application of these bitwise operators come in microprocessors, assembly language programming, that is microprocessor programming, computer graphics, and many more applications are there. Right now we have seen how exactly these bitwise operators operate on individual bits of the number. Thank you very much.